This variational method in quantum mechanics is based on a principle that the solution to a ground state or lowest energy eigenstate is the lowest energy, strictly the lowest expectation value of the energy, that we could possibly get for any choice of wave function. If you think about it, this statement is almost obvious. How could we get any answer lower than the actual lowest energy eigenstate? We can formally prove this statement fairly simply. So, in this variational method, we try some wave function, a trial function we call it, and evaluate the resulting energy, or strictly expectation value of the energy. Usually, in the way we set up such a wave function, we will have some parameter in it, such as an adjustable overall size. Then we will typically vary that parameter to choose the value of it that gives us the minimum expectation value of the energy. Perhaps the initial historic reason for this method was again the difficulty of performing fully numerical calculations. However, there are still good reasons to keep using this approach. First, it can often give us a quick method for finding some approximate solution, so we can understand roughly how some problem will turn out. Secondly, it can be a useful conceptual idea, one that we can sometimes use to eliminate possible answers altogether, as in, well, if you tell me you think that might be the lowest energy eigenstate, I can tell you that it can't be because I can propose another one that gives a lower expectation value for the energy. Another point that is perhaps less well understood than it should be is that there's a simple formal relationship between these variational results and energy eigenvalues, and we'll come back to that point later. So we'll start our discussion here of the variational method by proving the central idea that the lowest possible expectation value for the energy is the eigenenergy of the lowest energy eigenstate, no matter what wave function we choose.
So we'll consider an arbitrary quantum mechanical state, phi, and we will look at the Hamiltonian of this system, H, and we want the expectation value of the energy, E, as usual. Now, the Hamiltonian's a Hermitian operator, and therefore it has some complete set of eigenfunctions, psi n, and they will have associated eigenenergies, En. We might not know what they are, but we do know that they exist. Incidentally, here we assume that the eigenvalues are not degenerate, that there's only one eigenfunction associated with a given eigenenergy. Now, of course, we can certainly expand any arbitrary state in these psi n here, and so we can write as usual for our expansion coefficients, ai, just this summation here, ai times psi I, summed over all I, to give us the total wave function of interest phi. And we're going to presume, of course, that this is normalized, so the sum of the modulus squareds of these expansion coefficients have to add up to 1. Hence, the expectation value of the energy, rather obviously, becomes just the wave function in bra form, the operator and the wave function in ket form, and of course that's nothing other than the sum of the modulus squared of the expansion coefficient times the eigenenergy associated with that particular state. We also presume, incidentally, here that we've ordered all our eigenfunctions in order of the eigenvalues, starting with the smallest one. Well, if we look at this expectation value here, the smallest possible expectation value of the energy that we can have for any state is just E1. And why is that? Well, that is going to have A1 equal to 1. The first expansion coefficient is going to be 1, and all the other AIs are going to be 0. If we made any other expansion coefficient, such as some specific one, AJ, to be finite, then using our normalization sum here, where the sum of the squares of the moduli of each of these coefficients has to equal 1, the energy expectation value would have to increase. For example, here's our expectation value equal to the sum of modulus of A1 squared times E1, the first eigenenergy, plus the modulus of AJ squared times this jth eigenenergy Ej. Well, because of the normalization, A1 modulus squared is equal to 1 minus Aj modulus squared, because the sum of the two of these has to add up to 1. But that is just E1 plus modulus of Aj squared times Ej minus E1. And since this is a positive number, and this by choice is also positive because we said we had ordered all of these energy eigenvalues, then this is greater than E1. So therefore, if we add in any amount of another wave function in our expansion, we get a larger value of the expectation value. So the smallest possible value of the expectation value we can get is indeed the energy eigenvalue of the lowest state.
This property that the lowest possible expectation value of the energy is for the lowest energy eigenstate allows us to construct an approximate method of solution of quantum mechanical problems for the ground state, that is, the lowest energy state, and especially for calculating its energy. As we said, the key idea is that we choose some mathematical form of state called the trial wave function that is mathematically convenient for us, and which we believe reasonably fits at least the expected qualitative features of the ground state. And then we vary some parameter in this mathematical model to minimize the resulting expectation value of the energy. As a result of this minimization with respect to this variation, this is known as a variational method. If we use this method, we don't formally know how accurate our result is for the energy, but we do know that lower is better, and we can, if we wish, keep refining our mathematical form so as to reduce the resulting calculated energy expectation value. Now, why really would we use such a method? Well, first of all, it allows us to calculate an approximation for the ground state energy without having to solve for the exact eigenfunctions of any problem. A second reason is that if we're careful in the choice of the form of the function to be varied, so that the algebra of minimization gives us simple analytic results, we may get an approximate analytic result for some perturbation. Why does this method return even reasonable answers? Well, we can go back to a point we discussed in relation to perturbation theory above. We can get good answers for energies even with approximate wave functions. Remember that the first order energy correction in perturbation theory uses the zeroth order wave function, for example. The variational approach can be progressively extended to higher levels of the system if we force the next trial wave function to be mathematically orthogonal to all the previous, that is, lower energy ones. As far as numerical calculations are concerned, though, the variational method is nearly always used only for ground states. The easiest way to explain the variational method is just to look at an example. And for that, we'll use our potential well with our applied electric field.
So let's look at our example then of the variational method. We're going to use the same problem we've used to look at the various other approximation methods, and that's an electron in an infinitely deep potential well, but with an applied electric field. And we're going to use as our trial function here an unknown linear combination of the first two states of the infinitely deep quantum well. Now, more commonly, variational calculations will use some function that's unrelated to exact eigenfunctions of any particular problem. It will more be a function that's easy to work with, but not necessarily the solution of any problem. But for this particular case here, we're going to take this as an example trial function. So our trial function then is a sum of the first state and the second state of the unperturbed problem. We've put our variational parameter in here. We don't know how much of the second state is going to be in here. And then we have to carefully normalize this wave function overall. So that's what this factor is out front. And A var is the parameter we're going to vary to minimize the energy expectation value. Note that we've normalized this wave function by dividing by this quantity here. We must normalize these wave functions because we use them to calculate expectation values. If we're going to calculate expectation values and get them correct, we have to use normalized wave functions. Well, we can evaluate the expectation value of the energy using this integral here. And this is simply the expectation value. It's got technically the complex conjugate of our trial wave function here, the trial wave function itself over here, and the Hamiltonian operator. This factor out front, of course, is just the square of the normalization factor, one part from here, one part from here. And there's an analytic result that we can use to help us work this all out here, and here's that analytic result. Multiplying sine pi xc times xc minus a half times sine 2 pi xc. That's an integral that occurs a couple of times when we're trying to sort this out here. And that's got an analytic result. It's minus 8 over 9 pi squared. Also, we have to use our known unperturbed energies. Those will come up when we're doing this integral here. And of course, we use the orthogonality of these sine functions. So using these three attributes here, we can easily evaluate this integral here. And that will give us this particular answer. And what we want to do now is to find the minimum possible value of this that we can get by adjusting our variational parameter. So what we do is we take the derivative of this entire expression here with respect to a var, and that gives us the following analytic result. We've got a quadratic on the top line. We're going to find the zeros of this derivative by finding the zeros of this quadratic here in the numerator, and the root that happens to give the lowest value of this expectation value of the energy is this particular one here. So if we put f equals 3 in our example, we will find from our analysis that the value of our coefficient, a var, that gives the minimum for the energy expectation value is 0.175. And that compares with 0.174, which we got for this particular coefficient in the wave function when we used the finite basis subset method, and 0.180 that we got from the perturbation calculation. The corresponding energy expectation value from this variational approach we get by substituting this value of the coefficient that we figured out here back into our formula, and the result is 0.906 energy units, which compares with 0.904 from the finite basis subset method and 0.9025 from the perturbation calculation.
So there we have a simple example of a variational method. Incidentally, it can be shown that a variational approach like this, when using the same basis functions as a finite basis subset calculation, gives exactly the same results as that finite basis subset method. If we had calculated the finite basis subset method using only the first two basis functions, we would get exactly the same result as our variational calculation here. This is fundamentally because of the minimization property of eigenfunctions and eigenvalues we discussed before. The particular problem we've chosen to look at here is actually not a very typical one for the variational method, of course, and that method is probably not really the best way to approach this particular problem, but it does work. More typically, we may have no good idea of the energy eigenstates in any analytic form. Indeed, those eigenstates may not have analytic solutions, or they may simply be too complicated for us. We can then use the variational method with some much simpler function that we hope embodies the major features of the actual solution, and then get, as a result, a simple and usable approximate model for our system. For the ground state energies and the approximate wave functions, this can work really quite well.